Good morning, students. How are you? Mornings.
Morning, sir.
Are you ready? Are you ready for some work?
If it's easy work, then yes, sir.
Is it ever easy? It's easy. So welcome, students. This is our second last chapter. Oh yes, I think before I start, just give me a moment. Just came to me now. I meant to do this. Just want to get a slide here. Yeah, so before we proceed, just insert the text box here. Is two date. I've planned it for the 24th of May, which is on a Monday, the 24th of May. This will be around 11:30 probably. What do you guys call it? Close call. Helical spring? What to the chapter is? That's what the chapter is called, right? I'll just call it chapter 5. And chapter 5. Just get this. Probably put it in your calendar if need be. And this will probably be around 65 to 70 marks. I'll make it 60 to 60, 70 marks. Oh man, let me just get this right. Around 60 to 70 marks, yeah. So chapter 5 will be springs, 6 will be shear force and bending moment diagrams, and 1 will be trusses. That's chapter 1. This is what I've planned. If there are any changes, I'll let you know. But I thought by this week I'll already give you a final timetable. But I'll need to just you just have to be patient with me. But I've scheduled this test for this Monday. So your exams won't start at this particular time. So during that this is off the study week, so you get an updated timetable. So I'll just write the updated exam timetable. So please schedule this to be shared. Updated exam timetable will be shared. It is noted. Students, any questions? Okay, thank you. Thank you. Of course, you guys are preparing for ICN. But yeah, so what's good about this chapter is that it's fairly easy and there's great YouTube resources for you to practice, which explains. So I've put that at the end of the actual lecture, but I'll talk to you. Of course, I'll explain. But if you need more practice, I think the channel, the one of my favorite channels in Energy for Free has a as he also basically goes through a lot of problems, which will give you an idea of how to control this. Okay, that's just the announcement for now. So this will be part of your test 2 and obviously your exam. So, and these questions are normally 15 to 20 marks. So trusses and shear force takes a big amount of your exam marks. So please, for the next series of lectures, this week and next week, at least by next week, you'll be finished. They bulky marks. So if you can manage to do one, of course you should be able to do both. But I mean, like, just make sure you're able to do at least one. So each question is around 20. Yeah, okay, maybe each question is around 20 marks roughly, or not, maybe 10. But I know these sections, the marks are always got high marks, on 15 to 20 marks, and you'll see why. Nevertheless, let's move on. So looking at these two pictures, right? I should zoom with. What you see happening here? Just bring this one forward here. Does anyone have an idea? What do you see happening here? Can you guys actually see this? What's happening here? Anyone? Good morning. Morning. Wake up.
Yeah, so the load got too much and it failure occurred.
Yes, yes, yes. Can you see that? Do you know what this orange thing is called? Bending stress. That's good. What is that thing called? What are these two things called? The structure, so to say.
Beams.
Yes, called a beam. Right. Okay. So where I'm leading to here is, what's the purpose of doing shear force in bending moment time? Right. All right. Let's talk about it. So obviously, as I've had in the first lecture, I think the first lecture on stress and strain, is that what we're trying to do is, when we're designing something or anything, in fact, or particularly structures, we don't want it to fail. Right? We want our structure to remain standing for a long, in the excess of maybe 50 years or so. So the point of this analysis is, in particular, beams, right? What is a beam? So moving on to the next slide over here. Does that look, you see what happened to that? That looks like it buckled or something, right? That section. And of course, on the other side, that structure looks intact. But what I'm just showing you is there's what's essentially all here is beam elements. Few beams. Right, so let's talk about what a beam is. So a beam is a structural element that is capable of withstanding a load primarily by resisting bending, right? So I'm sure most buildings, I'm sure you've seen, and definitely on the ship as well. Most of these are beams, right? Just think of it as some, I don't know, some support, right? And what's important, okay, and then it says the bending moment is shear force induced in the material of the beam as a result of external loads. So we'll get to that, right? So the idea is that you've got a beam structural element, you apply a load on the beam, and you're going to get these two things called shear force and a bending moment, right? What they essentially just mean is, when you apply an external load on the beam, it's going to bend, right? And also it's going to want to shear. And you guys have the concept of shear, two parallel forces, opposite directions, you know, like a tearing force. So also the set of beams, remember, that carries loads transversely, that is perpendicular to its longitudinal axis. I'm just showing what a beam is, right? Or roughly telling what a beam is. What you see on your right is a typical I-beam, and there's a reason why the shape is like that. Now you only start doing true analysis in Strength of Materials 3, where you look at bending stresses and shear force stresses in beams, right? But for now, before we get to that actual part, we look at we're just gonna have to look at this concept of what happens when you load a beam, right? And I've just dropped a seed there, shear force and bending moment. Of course, you're kind of aware. Think of different types of beams, right? Different kinds of sections, as they say. You get an I-beam, you get a parallel flange, taper flange, you get angle iron, you get tubing. I'm sure you guys call it angle iron. They're essentially beams, right? And looking at the typical structure of a ship there, you can see that you've got a few beams, especially at, it's called the longitudinal frame there. They're all essentially made of a lot of beams. Beams and plates. A plate itself as well is also another structural element which you do analysis on. What is not really shown here is that you get different kinds of structural elements like a truss, if you want a beam, a plate is another one. But of course, we're focusing on beams, and I want to just keep it there. So we get different sections of beams, and I just want to quickly show you something. Just give me a second. And of course, these beams, which I probably did not say it's made out of steel. I'm just looking for a catalog quickly, which I'd like to share with you guys. Okay, maybe I could just. No, man, that's what I really want. So that we have an idea. Have you guys seen this kind of beams or structural elements before? On board, of course, or maybe dry docking or anything? Students?
Yes, Christina.
Yeah, okay. So that's what you call a beam, right? And of course, you get different kinds of beams. Into something. Yes, sir, of course. Yeah. I'm just looking, just bear with me. But anyway, let me just. I don't seem like I can get. I just want to get something, man. I'm inspired. I don't want to. Just not. This is all. Okay, this is some. Okay, there's a product catalog. Got something now from one of our. Nearly there, nearly there, nearly there. Aluminium. Is it oil aluminium? Steel, structural steels, nearly say. Different types, I guess. Yeah, anyway, I'll just go back to where I was now. To what I had initially. Okay, so one of our suppliers of steel here, and I say supply, they don't actually manufacture the steel, so I'm just gonna snip tool it. But what I'm what I'm particularly want to show you, let me just check with Drotsky. Just go back. Is for. I really want to show it to you. Next thing. Okay. Yep. There we go. So if you look at the back of the Drotsky textbook, you'll see these tables, steel section tables, and those are all essentially beams. I found one here, so I'll just quickly. Oh, okay. So I was here, not was there. Right, just duplicating. Yeah. So sorry about that. It's just that I really wanted to show you guys this. So this is from a textbook. However, if you actually get a steel catalog, you would get something of this nature, and it'll basically tell you a few things. Right? So we're going to be using the steel catalogs in Strength of Materials 3, but basically you get these catalogs, and I put it in a material certificate. That also would be nice, but you get it for various sections and it has specific data. So now maybe I should actually just get material certificate now as it is. Okay, material certificate IB is 355. Check off. Sorry guys, man, I just really wanna show you. It's really couldn't find material certificate. Okay, got something here. Got some of these Chinese material certificates. That may be good enough. Just one way we can identify the section, and then yeah, it doesn't really. Yeah, it's okay. Yeah, nevertheless, just want to probably show you this as well. Got something here. Yeah, got this at least. Yeah, just try to make this a bit practical. Because obviously, I've got some experience with this, and it just hit me now. Yeah, I'm here still. I'm still here. Don't worry. Oh, thank you, Annalisa. I really appreciate it as well. I mean, thank you for your kind words. I thought I'm sitting here. I just really want to show you some stuff, man. That's the thing. I appreciate your kind words, really. I just want to show you the kind of materials these beams are made out of, and I think that's important. So thank you for that, really. I guess the typical structure of steel you can get. Cool. It's just hitting me now. It's a thing, so I'm like, I have to show you guys. Okay. Of course, this is not limited to this, but anyway, I think I'm happier with this. Ideally, I'd have wanted a material certificate, but it's fine. So I'll just quickly revert back to our different shapes. Okay, just close up a few things here. Okay, great. So, yeah. So like I said, you get different sections, right? So what's worth noting is that these sections come in different sizes and they're used for different purposes depending on the shape. Different shapes have different second moment of areas, which is similar to your rotational inertia. But in this case, your second moment areas your resistance to bending. But that is not our core focus for now. What's important is that I want to show you this, right? So we get different sections. Second thing is normally the sections when you go to the supplier, they'll come in different catalogs, right? So you get, if you look at the back of the Drotsky textbook, you see, I don't actually want to pull up a PDF, but you get different sections. It'll give you all these dimensions and I and Z, E, and you learn. So I will be your second moment of area, just think as your like your rotational inertia for loading, and your ZE, which is your section modulus. You get this few different things, right, at different axes. But normally they are made from these typical steels. So you normally get S STL205 and ST55 steel grades, right? They are European designation. I assure you, I've tested, yeah, like over 100 of these steels. I can definitely promise you that. And these are the general steel. The normal steels you'll probably see is a ST55 or S25 steel, right? So just as like a slight just to so to go through it, and I won't talk how they actually the steel. But so what it basically is, to say that they can be bolted, riveted, and welded in a full range of structural and fabricated items, including bridge, box girders, cranes, and general structural projects. These steel grades are supplied with a variety of treatments and test options to ensure they are usable, highly usable in various projects. Anyway, so what's important on these steels, you get different grades of these steels, right? So to quickly explain to you. So this is the typical chemical composition of the steel. So when they make the steel, they have to ensure that it conforms to the standards. So now I'm digressing a bit away from it, but just to give you an idea of the steels. Anyway, so you get I'll just go to the bottom here, stuff I'm familiar with. So of course the chemical composition is dependent on how thick the plate is. But anyway, just go to the bottom. So we've got ST55 JR, for instance. So JR means it's impact tested at temperature of 20 degrees. Then we have ST55 JO, that's at 0 degrees. And you have ST55 J2, which is at -20. So we have not done impact testing, but that is a test, like I said, I've done a few times. But the whole point of that is that if specifically for like the maritime application, you should be aware that something called a ductile to brittle transition. And as steel gets colder, it becomes more brittle. I don't know if you guys are aware of that transition. I think the Titanic failed because of that particular thing. You guys aware of that?
Yes.
So, yes, great, right? So I just want to show you this graph as well. It's hitting me as well now. And this is only for, so I'm actually showing some metallurgy here. Funny enough. I think, but I still think it's important. So I'll just chuck him here. Yep. Great. So yeah, and then also before I get to that, I think I'm going all over the place, but you can see what a typical ST55 JR steel looks like. Your minimum yield strength should be 355. Your tensile strength should be around 470 to 630. That's your UTS. Your elongation is around 23%. Which of course should be ductile, and this is the impact test stuff, right? So when I'm talking about the ductile to the transition, so a normal low carbon steel, which is a normal mild steel as you guys know it. As you can see, as the temperature decreases, your impact energy becomes less. And what it means is that if it basically knocks into something, the steel will just snap. I mean, literally, it'll fail 90 degrees to the load or whatever. It'll be clean. It's a brittle failure. So what we do is obviously test steel at what is this? At 0 degrees and -20. I won't talk. Of course, I won't talk to that. That's a chapter on it. But I'm just making you aware that this is typical steel used for these I-beams, and before they actually get used, they got to go through some tests, depending on how it works. But they like I didn't mention of. But I don't know if I mentioned to you the process of testing. Yeah, I did actually, of the certificates. But anyway, that's that. So then you also get high strength structural steel. They basically, of course, these are more expensive. And their minimum yield strength is 690. Can't even bloody imagine. A tensile strength 940. So I'm just letting you know, in comparison, a UTS of 940 is what you can expect from a high yield structural steel. Of course, these will be used at like if you need big load carrying capacity. So you can kind of figure out the general steel will probably do this, but in a high-end application, you probably use an S90QL steel. Yeah, they give you examples, but just in essence, you've noticed the more strength the steel gets, and that's probably to do with more carbon, the elongation decreases substantially. However, they still considered ductile. They're also impacted at the minus 40 degrees, right? And they can withstand that. So yeah, anyway, so just to summarize, both all these sections can be made from those varying steels, the so-called beams, right? So let's move away from material science now. Guys, I just started throwing that picture over there. And this is basically a bridge they're building. And what you can see there is all those beautiful I-beams. And bear in mind, they are not taking these beams just by chance, right? It's a calculated decision for these things to stand forever. So what we'll be looking at basically is these beams, and you're applying a load on these beams. You can even see on the picture that these beams are joining their bolts. And yeah, anyway, that's what we're doing. We're starting with analysis on how to do it on a beam, right? What to make a beam, or what's happening in the beam when we're loading it up. That's what we actually bring out here. Oh, it's also very interesting. Did you know the propeller? I guess it's the prop shaft. I think it's the whole propeller shaft, right? What do you guys call this over here? The shaft is also called a beam, right? Of course, let's start with the ship, right? The ship alone is a beam, and as the waves are, I guess, they're rising and falling. They're also inducing so-called shear force and bending moments. They're making the ship actually experience those things. So in terms of the ship, the weight itself, it's a load, and then the buoyancy force acting upwards is also another load, and those two loads are induce those forces. Again, with your I guess, can I call it the propeller shaft, guys? I'm not sure that is correct. That's also a beam. Now, what I'd like to do, anything that carries a load over length, that's very nicely put. Maybe I should actually copy that here. Copy that. I like that. I'll paste it on my slides. Even I'm hoping to do, one of the chapters I want to do is actually in heat engines, is you actually do shear force in bending moments for shafts, right? And from that you can actually design a shaft using the things we've learned in Strength of Materials too. So making you aware, a beam is not only just a beam in terms of a structure, or it's anything that carries a load over length. Thank you, Mr. Kiefer. Thank you very much. So of course, you support the bearings in terms of this propeller shaft, and yeah, that could be your supports, and anyway, your couplings. I'm just looking at their bearings. That's your gearbox reduction. Okay. Anyway, it's just I think in NAVOC we actually do some shear force and bending moment diagrams as well. So I'm not sure if you guys done that yet, but just making aware anything that carries a load over length. So I just want to get that into my slides. So just get that in there. Just maybe say or. I should make that a bit bigger. We just got all here, right? Take in, put it over here. Just move it around like this. You can figure this out later on, but yeah. Yeah, that's what it is. Of a specific length. That's I really like that. Yeah. Okay, thank you for that. Let's get back. Okay. Now I'm gonna talk about, so it's kind of like a dip, but what beams are there? So how are you to the side? Let's get in the middle. So of course this is also in a textbook. So this is basically the basic beams you can get. Simply supported beam, you're right. So what happens here? They say this type of beam is supported. Of course, you're familiar with this kind of stuff. It's why you did moments in marine science, mechanics 1. So basically, beam with 2 supports will be the end, right? Not really much to talk about. It could be supported by either a roller or pin, right? We've discussed that. We've discussed supports. We've got a cantilever, and this beam is rigidly fixed at one end. So I hope you all get that. If you look at a typical aircon support, that is a cantilever. There's a lot of things which are cantilevers. Your typical shelf at home, maybe a free, what do they call that shelf again? Like a free floating shelf or something. There are so many things which are cantilevers. I mean, they're just cantilevers. A table could be a simply supported beam also. So I'm just giving you, making typical things in the office here that I can think of. Yeah, that's so many things which are cantilevers. Anyway, okay, cool. You also get an overhanging beam. So instead of the supports being at the end of the beam, like two extremes of the beam, you find them basically the beam overhangs on either end. I'll say like a seesaw. Does a seesaw work like that? No, seesaw is in the middle, right? Yeah, it is a bit of an overhang, obviously, right? And then we've got a bolting beam, right? Or incaster beam, right? Both ends are rigidly flexible. So they're basically like a cantilever, but both ends are fixed. So that's the four central beams we'll be looking at. Yeah, but the analysis we will be doing, and I will be saying this, is only on simply supported beams, cantilevers, and overhanging beams. We will not, for this level, we will not look at bolting beams. So I'm making you aware. Do not worry about bolting beams. Cool. Okay, I'll get to this soon. Then I want to look at types of loading, right? So when analyzing the beam, we have to determine the reactions, internal shear force, internal bending moments. Cool, right? We'll discuss what that is. Get to that. It is how to classify the loading, types of supports, type of beam. So we've done loading. Now we've done types of beams, right? So we're going to do loading now, right? So beams are subject to a variety of loading patterns. We've got a normal concentrated load, inclined loads, uniform disciplinar load, a varying load, and a concentrated moment. There's 5 types. Of course, there are more. And these are static loads, not dynamic, meaning they are not changing over time. They're actually just staying the same. So normal concentrated load, obviously you guys are aware of this. So let's say a normal concentrated load is one that acts perpendicular or normal to the major axis of the beam. At only a point, only carrying over small length of the beam, right? Then we've got typical ones. They show a nice example over there with a beam housing some pipes. So those pipes are actually loading the beam, and of course the weight induces a load within the beam, right? That is due to gravity, obviously. That's just a typical thing, obviously, aware of. You've got an incline load. So incline concentrated load is one that affects actually effectively at a point, but whose line of action is not at some angle to the main axis of the beam. So it's a simple thing here. So we've got a hydraulic cylinder and we've got a spring arrangement, and what they're saying here is the spring itself is at an angle to the actual beam, and that's a typical incline load. So that the spring loads the beam, but at an angle. So of course, in this case, essentially, we're all just taking components. That's all it is. It's like that looks like a 60-odd degree line or 70, 65-degree line. Yeah, and that's loading the beam. Okay, so we've got a UDL, uniform distributed loads. You guys are probably aware of this. Loads of a constant magnitude acting perpendicular to the axis of the beam over a significant part of the length, or uniform distributed loads. So what they're showing here is like maybe a factory of some sort, and you've got, let's say you've got some snow, snow like on the top of the roof, but it's uniformly distributed, so it provides an extra amount of load on it. One could even, yeah, that's a yes.
Are you
Go for
able
it.
to invite someone into the class?
I'm not with you. I can maybe. No, but like someone's stuck.
Yeah, Matthew Doyle can't get in.
Oh, what's happening?
He said he's not able to get back.
I'll just have a look quickly. Session is open, so I don't understand why. Can you just use a link again?
Okay.
Like what's happening with the link? I'm not exactly sure. give that a second. Is he trying to get in? Yeah, I can see he's joining now. He's joined. Matthew, welcome back. What's the problem? It seems your network is a bit poor there.
Yeah, so
Yeah.
I've switched onto my phone data now. I don't know why my internet's
I
gone
see.
so bad all of a sudden.
Yeah, okay, yeah, I can see your network strength on the side. Analysis is quite strong, and Mr. Hermanus as well. Jason Graham, Hermanus, and Ushe Leroy, they're all good. Yeah, but yours is like 4 bars. Okay, so that's what a UDL is, right? So you've probably seen what a UDL is. What's probably new to you is a UVL, and it's a load of varying magnitude acting perpendicular to the axis of a beam or significant part of the length. So it's important, significant part of the length for the UDLs, and for the typical concentrated loads, they normally over a very small part of the length of the beam, right? So UVL, we're just showing you a typical thing there where the snow is kind of basically it's a cantilever kind of arrangement, and the snow is like not uniformly distributed. It's like a triangle basically, and that of course that's a different kind of load. You've also got concentrated moments is another load, and this is essentially you need to just quickly read. A moment is an action that tends towards rotation of the beam, right, of an object. So moments can be produced by a pair of parallel forces acting in different directions. So saying that, and of course that is called a couple. They're saying the action on the crank or lever produces a moment, and when a moment acts on a beam at a point in the manner that tends to cause rotation. But basically it's just force in different directions, and there's support over there, and it essentially makes a beam when it rotate. It's like shear or torque kind of force. I think we've got an example there. So we've got a gear and a supported, and they say there, so we've got a shaft carrying a helical gear, and the force F acts parallel to the axis and of the shaft and tends to bend it in the plane of the page. So that force, the tangential force acting parallel to the axis, the force times the distance is actually producing, it wants to bend the beam, is downwards in this case. So the difference here is that there is an unbalanced or horizontal force also applied to the beam that must be reacted to at one of the supports. Anyway, so you also get a moment on the beam. Okay, just more talk, unfortunately. And what we're just talking about, we get different kinds of supports. One would be a simple or roller support, and I say a simple support is one that can resist only forces acting perpendicular to the beam. So that's cool. You've touched supports before. You've also got a pin support, and the pin support basically means that it's free to rotate about the axis. And let's say an example of a pin support is a hinge, right? That can resist forces in any direction, but allows for rotation of the axis of that, right? So you know what that is. You've also got a fixed support, right? And let's say a fixed support is one that's held solidly, you know, it's a word. Oh, it's fixed, which is the force in any direction and also prohibits rotation of the beam. So of course, a simple or roller support, you know, there's only a vertical reaction. Whereas a fixed support has both a vertical and a horizontal. I'm sure you guys have got kind of experience of that. So that is just what these different supports are. So heading on to the official part of the actual lecture. You know, it's a lot of talk here, unfortunately. Let myself, yeah, we're getting close now. We're getting close. We will be doing a lot of examples. Yeah. So, taking all of that information, getting back to beams, right? Now we know what a beam is. You can see there's a roller support and we've got a fixed support, right? So let's see what happens. So we apply a load on the beam. So let's say when a beam is subjected to loads, bending stresses and shear stresses will be induced in the beam, causing it to flex. What this means is that when you take a ruler, right, and maybe you put two supports on either side of the ruler, I don't know what supports, maybe to be raises, as to low, something about higher, right? And you're applying maybe your finger, and assuming the ruler is attached to those supports, you're applying a load on the beam. What's happening? Two things are happening. The beam is gonna want to bend and break, or the beam wants to shear, right? So we'll talk about that, right? So now they say that the value of the maximum shear stress is negligible compared to the maximum bending stress. That's very interesting. In most of the cases of shaft or beam design, quite important for joint design, bolts or rivets. So what I'm going to tell you now is that for longer beams, and I'm not sure of the specific length, I'm talking about a substantial, maybe even a meter, that could be long enough. Beams are more likely to fail in bending versus shear. But if you take a shorter beam, and I'm talking a very short beam, maybe a small ruler 500, for instance, you support it on the table, you clamp, you put your one hand on the table, and you try to actually bend the beam. I don't fail by bending, but it'll completely shear off. So for shorter beams, shear is more predominant, but for long beams, bending is shear failure is more predominant in shorter beams. In longer beams, it's to be bending. So of course, bending is the most important thing when looking at beams anyway, before you're designing beams. So I'm talking about failure, and I want to talk about what kinds of failure one can expect in the beam. So I probably should go back now and I'll talk about that failure. So there are 5 typical failures. So let's say beams normally fail due to, in fact, bending failures, which is discussed in the chapter as part of the other thing I had. The Strength of Materials 3 we have introduced this. Whereas others are shearing failures, exactly what I said. So bending and shear stresses are both inherently present in any beam. So that's very important. And that is where the whole analysis comes. So which type of failure actually occurs first depends on the loading pattern, right? How the load is you've got a UDL, you've got a concentrated load, there's a moment, etc. The material from which the beam is made of, right? Depending ST55 J R, S90QL, maybe it's you ever get a stainless steel beam, just say stainless steel 304-316. The shape of the cross section, maybe a channel, a U channel, L channel, I beam, parallel flange, staple flange. And the actual dimensions of the beam, of course, you get different sizes. Yeah. So there are failure modes: the complete fracture, yielding, local crippling, web crippling, fastener failure, and interlacier. So this one is I'll talk about complete fracture. So the material beam should be somewhat brittle. The cross section should be small enough to break under moderate loads. This is a classic example of such a beam. I'd like to ask you, what kind of failure is this? The shear or bending? So that we're aware now, there's 2 kinds of failing, shear or bending. Which one is this? So chalk, think of chalk, got a piece of chalk, you break it, what is that?
Yeah, it's a shear. So.
Fantastic. Yeah, fantastic. So that's a typical shear failure. So if you're dealing with a more brittle-like material, it's most probably going to fail in shear. Fantastic, guys. I'm glad you guys are getting this. Now this one, let's say the yielding part of the beam, so the material should be ductile, so it will deform prior to any tearing of the material. Small metal rods with a variety of cross-sectional shapes, thin flat metal beams, small plastic beams. What do you think is this one? So you've got a beam, maybe a small plastic ruler, and you keep on bending, not a small plastic, maybe a 300 mm ruler, and you bend it. Or is this shear or bending?
It's bending.
Fantastic, fantastic. What you're seeing in this particular section here is the beam passes yield strength basically. So let's assume a yield strength of 355. You're seeing this beam with induced stress of around say 400 megapascals. So that's why it's not completely broken. However, if you keep on loading the beam and let's say the UTS is around 500, it's going to break. That's the idea. So that's fantastic. So you can see a typical shear failure, typical bending failure. This is interesting. So local crippling is what I had over here. Ugly picture. And one. Another form of failure, right? And this could be a combination of stuff. So there's local crippling, there's web wrinkling, there's fastener failure, and okay, there's interlaminar shear. But just to, I don't want to spend too much time on failure because I'm not essentially going to assess you on these things, but just to give you a nice backdrop of what you're trying to achieve here. I don't think the book does a very good job of this. Is basically shear is also important, but shear, get shear there. So you have wrinkling of the web. That is due to shear, because we will discuss all of those things. And then also, where shear is really important is when you're looking at your joints. That is where shear really becomes important. And even with bolts itself, bolts fails in specific ways. There's 3 different ways. And that's joint analysis or bolting analysis is something completely on its own. So anyway, just to give you an idea of what's happening here. So again, back to where we were. We have a beam, we load it up. Now we know we get two battles. We get a shear battle and a bending battle. And depending on how long the beam is, one is more predominant over the other one. Right? Fantastic. Cool. So what do they say here? They say prior to studying the actual shearing stresses and bending stresses or forces, this chapter helps you to visualize and compute values of internal shearing forces and bending moments themselves. Right? That's what we'll be doing. Each is dependent on the nature of the applied loads of the beam and the weight supported. Yeah, we've got that. So we define shearing forces as shearing forces are internal forces developed in the material of a beam to balance externally applied forces in order to secure equilibrium of all parts of the beam. Beautiful. Beautiful. It's internal forces to resist the external forces, or not in order to resist, but to secure equilibrium of all parts of the beam. Whereas bending moments are internal moments developed in the material of the beam to balance a tendency for external force to cause rotation of any part of the beam. So these are all internal forces, right? Every reaction, the reaction you applying a load, excuse me, the reaction is going to be a shear force and a bending moment, right? And I have some differential equations over there, but just for show, because you guys will be touching on that on Strength of Materials 3. Anyway, just some important things to know. So this is very important. So they say the shear force and bending moments are very important factors in the design of a beam. Kind of we've highlighted that. From these values, horizontal and vertical shear stresses influence the strength of welded, rivet, and bolt joints, bolt up section, and bending stresses determined. There we go. So always think of shear stresses more for the joints, whereas your bending is for the beam itself. So just some notation. This is shear force and bending moment diagrams are used to visualize these quantities. Now that is the central premise of this chapter. You will be required to sketch shear force diagram and bending moment diagrams, right? And also what is important, we're able to locate the position and magnitude of the maximum shear force and the maximum bending moment, along with point of inflections or points of contraflexion as well. So just standard notation of what's happening. A positive bending moment will make a beam upwards. A negative bending moment will make it bend. I don't know. You get the idea there, right? But I'd rather say it like this. Positive bending moment will induce a tensile, a compressive stress on the top of the beam, whereas the bottom will be a compressive stress on the top, a tensile at the bottom. Negative would be a tensile on the top and a negative at the bottom. Shear force, yeah, it's all over there. But what's important here, I want you to take note of, and this will not be given to you in your formula sheet. You have to know how a typical shear force and bending moment diagram looks like of each of these guys. So what you'll be looking at basically is a simple supported beam with a central point with a UDL, and then you could have or the end point and with a UDL with a cantilever. So cantilever, some supported beam are the 2 things you need to master. And they all have their own different kind of shapes, and you'll see how it basically works. So you do get marked on the shape of the thing, the magnitude and the shape of how the thing looks. Okay, so this is from one of my favorite channels on YouTube, the Energy Efficient Engineer. At the end of the slides, I've posted a link of these videos. I'll place it on there. So I highly recommend you watching it. I think he explains things way better than myself. And this is what a typical shear force and bending moment diagram looks like. And if you just looks at it, so we've got an I-beam over there. And of course, you guys just see these. What beams are you looking at here? These boring looking beams, like a straight line or some rectangle. So the beam actually looks like that. Supported on both ends, so therefore the simply supported arrangement. It's got a UDL and 36 kilonewtons. So we're just looking at the beam. We end up sketching these diagrams, which you'll be able to do at the end of this module. And you can see your maximum shear force is, what's your maximum shear force there? Look at the shear force diagram. Is there a 50, right? It's like a minus 50. Do you see there? That's a minus 50 over there, and your maximum bending moment is at 128. So those two particular points, or that over the what's it after the 8 meters going into the beam, there is where your maximum shear force occurs, right? So if you're going to be designing a joint, wherever you're putting those joints, you need to be aware where you want to put it. So that's the purpose. So you can basically locate where you want to put your joint of the beam. So if you look at your bending moment diagram, and what's kind of funny, your shear force, when your shear force is typically 0, your bending moment is normally at the maximum, and we'll discuss that shortly. And at that particular point, you must be careful where you'll be applying anything, because that's where the beam is most likely to fail. Your bending moment is at the max there. So that's the kind of way you want to view it. Was it clear to everyone? I never talk so much with slides. Yes. You guys get the idea of what a shear force and bending moment diagram actually is when you're looking at it?
Yes, sir.
Yeah, thanks. Anyway. All right. Okay, so yeah, guys, we're basically there now. Okay, so before we start, let's just give a quick 5-minute break, or let's start at 10 past 11, and then we'll start on our first example. So just grab yourself a coffee or some water, and then we'll start actually on we'll be looking at our first example. So after this, we'll just be going through examples. But I really felt that I wanted to do justice for you to explain. So I mean, look at this diagram. The diagram doesn't tell you anything. It just looks like a small picture, But I really wanted to explain to you what this is all about. It's a very, very important thing in structural engineering. Okay, guys, let's reconvene at 10 past. Just grab your coffee, get a snack, and we'll be doing a lot of examples now for the rest of the day, basically. Okay. See you shortly. So we're going to start now. So what I'll first do is do a typical shear forces bending moment diagram, go back to the slide, do a small explanation based on these values, and then yeah, and then basically you have a full picture of what is required. So guys, I'm just giving you 2 minutes. Are we all ready? Are we all good?
Yes, sir.
All right, let's begin. Sorry about that. I was just preparing my coffee there. Okay. Students, can I get a few thumbs up? Just thank you. Sorry about that delay there. Just want to get this right. Okay. So we're going to be doing A and B. And then going back to the slides and then determining C. Right? I've got to get some coffee to get myself warmed up here. So how do we start? So the first approach to these problems is finding all the forces, right? Okay. So we've got a simple overhanging beam, and we've got two forces acting upwards, right? So now we know we've got, we're looking at the so-called perpendicular forces to the beam, the perpendicular, yeah. You've got RA and RB. All right. Students, are you there?
Yes, sir.
Great. Okay. So the first step is we need to find RA, RB, right? So if you remember the approach, second condition of equilibrium, we got to take moments. And so what we can do, we can take moments at B, right? So B or B, it's A, B, C, D, E. So I want to make you aware, if your beam is not labeled, right? Label your beam. Now normally your beam is always labeled, so I'm just making you aware. And this is for the sake of ease, so when I assess you, it's possible for me to actually just figure out exactly what is what. But we take moments at B. Of course, we could have taken moments at the other support as well, but we're taking it at B because we want RA. So what do we do, right? So we start on the 15 kilonewtons. 15 kilonewtons is going 15 times 1, 2, 3. That's going anti-clockwise, right? Oh, no. Let me just get this right. Moments at B, so that's minus 15 times 1. RA will be 0 in this case because so sorry, this is RD, yeah. Then we have C, but C is going clockwise, so that's plus 80 times 1. Okay, and then we have RD now, that's RD is going anti-clockwise at RD minus 2. And lastly, we have 10 kilonewton, that's 3 meters away from them, that's also going clockwise, plus 10 times 3. All we have to do now is solve for RD. So we have RD, we can carry RD over to the other side. And then we have minus 15 plus 80 plus 30. Can you guys solve RD for me quickly? What is RD?
47.5.
Fantastic, right? I hope you guys have to do this. So let me tell you something about shear force and bending moment diagrams. If you get your reactions wrong, you're basically going to mess up the whole question. So it is your responsibility to make sure you get the right reactions. Wrong reactions, no marks. So very important. So for us to find RA, what we can do is take moments again, right? I'm gonna just show you all the ways you can approach so you can make sure that you're correct, and that's up to you. So we need to take moments at D now, right? We make that equal to 0. So we're taking moments at D now instead of B. So then we go minus 15 times 1, 2, 3, right? Then we have, that's clockwise, so we have RB times 2. Then that's also going anti-clockwise, that's minus 80 times 1. And then lastly we have, that's going clockwise, plus 10 times 1, right? That equals 0. We solve for RB, then we get 2RB, that equals 45. I'm carrying this over to the other side, plus 80 minus 10. And what is my RB equal to? Is it RB? Yeah. What do we get?
57.5.
Okay. You guys agree with that? I hope you guys calculated it. Yeah, 57.5 kilonewtons. Okay. Alternatively, what you could have done is, or you could have said RA plus RB. So forces up, which is forces up, equals forces down. You basically add 15, 80, and 10, right? So that's 80 plus 50 plus 10, gives you 105 kilonewtons. And of course, what you're expecting is when you add RD and RB, you should get 105. So make sure your forces balance. If it's not balancing, it's a problem. I've seen several students have problems with this kind of thing. And it is unacceptable because this is covered in the first level. So if you, let's say you didn't do this step here, you could have just said RD was 47.5, that equals 105. You want to solve for RA. If you're sure, you say 105 minus 57.5, that's 57.5. That's if you're pretty sure. Okay. Is there any questions with this? Finding your reactions, because this will be second nature. I won't be doing this the whole time. This will be up to you. I'll do it for probably the first 2-3 examples. Subsequently, I will not be solving this the whole time. Is there any questions or finding reactions? I hope you guys are able to do it. You can just get some thumbs up there. Students, any questions? All right. So now, once we have our reactions, we have to draw our load diagram now. Okay, thank you. Okay, so I'm just gonna, let me just copy this beam again. So that's our first step to solving shear force and bending moment diagrams. You will get marks for that. I can definitely assure you. And now this is where the new work starts, right? Okay. Won't or will? You will get marks for it. Yeah. So what happens now? So now what we just gonna, so what do we do now? I'll just probably do these white lines. You know, we want to just draw lines in line with each with A, B, and C and D, and you'll see why. This is the approach, right? To make solid line, I'm just doing that, and then at some point, I'm just going to keep going down. At some point, you just want to make a perfectly straight line. Oh, well, perfectly straight. This will be your 0 point here. Okay. I'm just trying to figure out how to use my ruler. Let me just quickly see. How do I rotate my ruler? Oh, sweet. I know how now. Give me a second, guys. Just give me a second. Yeah. So the first step is, of course, draw these lines. And then what I'm going to do now, well, oh, a bit. That just felt very good now. I managed to do a straight line for the first time. Okay, beautiful. We've got that down. So, okay, now we have our forces over here. We've now our RB force, and our RB force is at 57.5. Of course, you can draw a separate diagram for this with your loads acting on it, but I'm just kind of lazy, so I'll just do that there. Okay, so how do we find the shear force? So we look at each section, right? So we start at A. So what we just basically do, we look at all the forces acting on the beam at a particular section. So here we have 15 kilonewtons, right? But that's going downwards. At A we have minus 15. So we have to make sure we get our signs all right. So the force is going upwards, then we have to say plus. So at B we have minus 15. The force acting at B plus 57.5, right? And if you do that, minus 15 plus 57.5. So I think a better way of me actually saying this to you is that's 42.5 kilonewtons. What we do is look at a section on the beam and then add all the forces from the left-hand side to the right-hand side, basically. So I'll say that again. So you look at a particular section. So if you look at A, right, there's nothing obviously on the left-hand side, so it's only 15 kilonewtons going downwards. If you look at B, you've got 57 going upwards, and then you've got 50 going down. So we keep on looking at the forces to the left. So it's C. Can you guys give me the forces at C? Can someone just shout it out for me?
Yes, we have 80 kilonewtons down, 57.5 up, and 15 down as well. So essentially 95 down and then 57.5 up.
Thank you, boss. So in total, we have how much? What's all of that?
Minus 37.
Minus?
Minus 37.5.
Are you sure? We are at C, right?
Yes.
Right. Oh, yeah. Minus 27.5. Sorry, it's my mistake. Yeah. 37 to 27. Yeah, negative, right?
37.5.
Yeah, signs are important. And at D, we do exactly the same. So now we have, I'll just start at D, 47.5, going this way, minus 80, plus 57.5, minus 15. What do we get for that? We're nearly getting there. Minus 80, plus 57.5, minus 15. 10, right? I get 10. Positive 10. And at E, what do we have? 10 minus 10 plus 47.5. What is it again? Minus 80 plus 57.5 minus 15. But you know we're going to find out, and we're going to see now. So now you're getting some experience with shear force diagrams. We should get 0 at the end of the beam. Are we all happy?
So why did we plus 15 at C?
Lisa, let me see. Oh, it's a mistake, man. That's why. That's what I wrote down. That's why I was getting the answer. Thank you. Are we all happy? Students, can I proceed to draw the diagram? Students.
Yes, sir, you can roll. You can roll.
Okay, thank you, man. Guys, please, man, be interactive. So what you must be cognizant of, right? Whether you must paste this in your textbook, print it out and paste it, is that the diagrams must look like this, right? So if you have simple loads, your shear force diagram will be just basically lines going up and down, like lines going with, horizontally across and all of that. So you need to be aware of of your diagrams when you draw. So when you're done doing the diagram, you need to be aware of how the shapes of the diagram look like, right? It'll be fairly easy to remember, but of course with time you get some experience. So this is work on your behalf. All right. So how do we draw it? So I'll use bread. At A we've got minus 15, right? Okay, so I'll say minus 15. I don't really like. Okay, so I'll just say, so of course this is X will be the length of the beam. I mean, this is the length of the beam. And just bear with me. So I'll just say minus 15. It carries on from here till here. So what this means is the beam experiences shear force of minus 15 kilonewtons along that part. But when we come at B, it goes up. Right? Of course, it doesn't have to be to scale as long as it shows it's higher up than the other one. I think that's at. Let me just go back again. That's at around 42.5. And then it stays constant till C. Then what happens at C? We're down at minus 37, so we have to go all the way down again. It's lower than that. So this is minus 37.5. And then we're going at D. D is at positive 10. And then eventually, we know we're doing well because if we can across, you see you got a negative 10 at the bottom, and the negative 10 is going to push this down to basically 0. Right? And that's our shear force and bending moment diagram. So how your marks will work is probably 1 mark there, 1 mark there, 1 mark there, 1 mark there, and then probably a mark for closing and maybe a mark for the shape. So 1, 2, 3, 4, 5, 6. I'm at 6 marks. So make sure on your diagrams you have the correct values as well. That's very important. Give me a second. Students, just give me 5 minutes quickly. Sorry about that. I'm back. My apologies. Okay, right. So we've got the shear force and bending moment diagrams. So sorry, this the shear force diagrams, and now we have to draw the bending moment diagram, right? Okay. So again, just looking at the analysis of the beam. So we can expect a maximum shear force at position B with a magnitude of 42.5. So if you look at question B, one of the things to do is to find the position of the maximum shear force in bending moment diagram. So I'm just making you aware that's normally for 2 marks each, right? So let's get the bending moment diagram. Let's see how we actually are able to do that. So I'm just gonna get my lines down again. Okay. Normally just want to use the same kind of beam. Just want to get the ruler again. Bring the ruler down a bit over here. And 0. Okay, just away from that. Okay, that's done. So 0. Okay, students, are you still there? Oh. Students,
Yes, sir.
oh, thank you. Yeah, sorry about that. And something but urgent. Okay, so how do we draw the bending moment, right? So all we have to do is take moments at individual at each section, right? So maybe I should do it over here. So moments at A, right? So of course at A, the sum of moments will be 0 because there's no real forces. Well, there's no real forces. There's no forces really. All the forces acting at a particular point will be 0. Once again, we're also moving from the left to the right. I didn't want to discuss the procedure first. I rather want to just start it and then get back to the slides after this. So then, now I see the book has a different approach of using moments. Obviously, you can use the approach, but I do it differently. But the idea is I can basically so taking moments at B now, right? So when you're at B, it's minus 15 times 1, so that is going anti-clockwise, and then that's basically all. And then we have 15 kilonewtons, okay? Minus 15 kilonewton meter, right? That's at B. We do at C again. So at C, you've got, I keep on saying 0, but it is equal to 0. But anyway, so it's minus 15 times 2, and then we have plus 57.5 times 1. And if you add those guys up, you'll get 27.5 kilonewtons, right? This is my approach of doing it. I prefer this one. Maybe I'm old school, but there is a much more easier way to do all of this. So hope you guys got that. 27.5. So taking moments at D now. So that's going to be minus 15 times 1, 2, 3. So that's 3. Then we've got plus 57.5 times 2, 1, 2, and then we've got the 80 there. So that's I'm gonna have it under here if you don't mind. Minus 80 times 1. And if you add those up, you should get what is this? Times 57.5 times 2, and then you're gonna have minus 80. You've got minus 10, right? Minus 10 kilonewtons. And always more than often, if you do exactly all the shear force at the end of the beam, your moment should close up to 0. Right? I'm not gonna actually you can actually check it out yourself. Students, is it all clear? A, B, C, D, and E, right? 0 kilonewton, there, and there. Students, are you all happy with this?
Yes, sir.
Okay, thank you. So what do we do now is literally sketch. So again, you must be cognizant of the diagram which I mentioned, right? So for beam with this concentrated loads, I'm just gonna move down here. We just have to draw these so-called straight lines, right? They are essentially straight lines. So it's this So we have a UDL, our bending moment diagram of a curvature shape or parabolic shape rather. Okay, so we know this is all going to be straight lines for now. So at 0, so we have 0 over here. That's minus 15. So we can have minus 15 over there. I'm not going to put the unit obviously as kilonewton meter. Then we go up to 27.5 at C. Oh no, where are we now? Yeah, because we got, so at C, we got up to 27.5. Then at D, we go to minus 10. That's around this, yeah, maybe that's minus 10. And of course, we're going to end up closing the diagram. Diagram should always close up like that. Okay. Are we all happy? No, these are perfectly straight lines, by the way. So I'm just making you aware of that. Are we all happy with this? Okay, I'm assuming we are. And then the next question, which is B, let's get that for you. Find the position and the magnitude of the shear force in bending moment diagram. So when I basically mark, I basically look at those values to see if you're right and wrong. Of course, if you didn't get the right values, I would have probably figured out exactly why. So at B, what we do now, say Vmax, say Vmax or Mmax. So you get 1 mark for the magnitude. So it's at, it's 42.5 at B, right? At B? It looks like it's at B, yeah. Let's say between, I guess, C and D, but, oh, yeah, just call it at B. I'll save that for the 2.5 kilonewtons at B, right? The maximum moment will be 27.5 kilonewton meter at ABC. All right, and once again, 1 mark, 1 mark, 1 mark, 1 mark, probably 1 mark there, 1 mark there, 1 mark there, 1 mark for the shape, something around that nature. So we already have, oh, and the marks of the actions, right? So you probably definitely get 2 marks here. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So around 18 marks here. 4, 8, 12, yeah. Makes sense. We can see how big these questions are in terms of marks. It's essentially marked similar to this. Okay, are we all happy with this? That's your first shear force in bending moment diagram over there.
Yes, so happy.
Okay, great. Thank you, Elisa. Now I just want to revert back to the slide. Like I said, just to just kind of complete the theory component of the actual lecture or talking, as one would say. The only things what's worth noting on your diagram, and this is very important, right? The first one is at the point where shear force diagram passes through 0, where the shear force sign changes, the bending moment's either a maximum or a minimum. So that's very important to note, right? So there's a relationship between the shear force and bending moment, right? So you must know the shear force is 0, the bending moment is at a maximum or minimum. It's always going to line up like that. If it's not lining up like that, there is a problem. So I'm making you aware of that, right? Normally, the shear force is 0, you find the maximum bending moment. That's normally the idea. Also, what they're saying is that over any part of the span of the beam, the shear force 0, the bending moment has a constant value. And normally, when the shear force is 0, and if you plot the stress distributions of the actual beams and stuff, you'd actually see it's true. Now, I might have a picture for that. Maybe I'll get a picture when you break again. But that's important to note. Shear force 0, maximum bending moment, right? That's normally the case. And what's another important thing is something called the point of contraflexion or the point of inflection, right? So basically, at any point when the bending moment passes through 0, when the bending moment sign changes, the curvature of the beam changes. So basically, going from a negative bending moment to a positive one, and there the bending moment is 0. What's important about that bending moment being 0? Why do you think that's important? To locate the point of contraflexion. Just thinking from a practical perspective. Why do you think we need to know the point of contraflexion? So that is where the bending moment is 0. Why do you think you need to know it? Just have a small thought about it. Anyone? Quick.
Is that where the maximum bending stress is going to be?
No, remember, if there's no bending moment, there's no bending stress. Right? That's the first thing. No bending moment, no bending stress. So what I'll do for you now, I'll tell you why. And this is a very important part to remember. There's an extra two or three marks. Okay, so I'm gonna make a new slide here. Now, and I'm definitely gonna plot the distribution within the slide. So what it is that beam section available in certain lengths. Okay, so if a beam is very long, it should be joined at the point of counterflexure, right? As this will prevent the joint from being subjected to bending stress. Because if you putting a joint along, so like heading back to this beam here, remember this beam, the long beam I had with this beam over here, and as joined at particular sections. Let's just quickly have a look. Where's joint maybe? Can I just zoom this guy maybe further? Yeah, maybe a bit more. Okay, now that didn't work out well. But it's essentially joined at, I don't know if you guys can see. It's also like basically where bearing support is. So maybe like that. So you can see it's joined over here. It's obviously going to be so long. And then you have to eventually join the beam. So over there, they join. Of course, it's all joined in the same place, but that's we ideally don't want the joints, which is in this picture over here. Let's say for argument's sake. I've zoomed this picture. That's like these joints over there, or maybe something like that. We don't want the balls to experience that. So that is why we need to find the point of contact. I hope that was clear to everyone. As to why it's important. Is that all okay? Do you all get that? What's important on the point of counterflexure? So there are 2 points. When the shear force is 0, maximum bending moment. When the bending moment is 0, we have the point of counterflexure or inflection, which essentially means that is where ideally we want to join the beam. It's not so simple in practice, but it does provide us a good thing. Okay, so based on that, now we can find C, which is the points of counterflexion, right? So let's quickly revert back to our whiteboard and then find those points of counterflexion. All right. So looking at our diagram, we have where are we here? We have, so we have to look for the point of counterflexure. So that's the bending moment is 0. So I have maybe blue. And if you look at it, that's over here. There's one over here. Oh, no, wrong color. Blue. Let me make it purple. Not purple. Something more yellow. Over there and over there. Right. Are we happy? You got that there. Okay. So how do we find it? We call this distance. I'll just call this X maybe. And I'll call this guy Y on the other side. What we essentially do is take moments to that point, right? That's what we're going to do. So I'm going to say moments about X, or I'm calling it distance X, but let me call it X and Y. Or moments about that point. Doesn't really matter what the point is called. Yeah, I'm just going to call it X and Y, and just bear with me. And if we take moments about that point, we've got to look at our forces over here. So if you look at it, we've got minus 15 times X, which is that whole distance. And then we also have this piece over here. This piece over here. And that is, of course, 1. So what is that distance over here? Is it 1? Is 1 minus x maybe? What's a load diff? Plus 57.5? No, what's it plus 57.5? Yeah. Oh, my pencil went away. So that is 1. X is over there. There we go. Plus 57.5. I think that should be x minus 1. Students, are you following so far? I'm using moments to locate where the point is.
So I understand why you're using moments, but I don't know why we're using 57.
The reaction, remember, so this is not perfectly, look where x is. X is between A and C. Go for it.
So now we are using the reactions, not point A, B, C, D, and E. Just
So
the reactions.
go. Yeah, no. What we're doing here, we're looking at all the forces.
Okay, all of the original forces acting on the thing, not what we've resolved to A, B, C, D, and E, but all the originals.
Yeah, no, but yeah,
15.
basically till this point. All the forces till this point.
Okay.
Are you with me? Yeah. Just check.
Okay, so what we would use 15 kilonewtons, 57.5, 80, 47, and 10.
Yeah, no 80. Just these forces. We can neglect the other forces on the end. Don't worry about all these forces here. Your thinking is still right, but don't worry about it. Yeah. So don't worry about. So just work on all the forces to the left. Yeah. So then now we take you home. So I ask you, you agree with me that this distance here is 1 minus x. This piece here. Let's see if people get tripped out on me. So they've called it R over there. It's 1. So let me just get this. Measure this. Just want to touch it quickly. This is where students normally get tripped out. So let's copy this. Place it over here. Okay, so we've got a nice neat diagram. So we're finding this and that there. I'm just quickly solving it here. Are we all on the same page over here?
Yes.
Yes. Yeah, so. Oh no. Instead of me doing that, sorry, where am I? So we're saying, well, let me just take this. Just get it neater now. So we're finding this, okay, we're going to call it R for this argument's sake. So we're taking moments at this point here. So we have minus 15, right? It's minus 15. All right, I'll just make minus 15 here. Kilonewtons. And then I have the other one, the other force there, right? That's 57.5. So we know sum of moments at yellow point, at yellow equals 0. So I'm saying minus 15 times 1 plus R, right? Does it make sense? It's 1 plus that R distance. You guys see it? Okay. And then we have plus 57.5 times R, that equals 0. Do you guys see that? You're taking moments at this point R. Students, it's very important for you to just let me know if you're able to get this or not. This is an extra marks.
Okay, so as a question, you can also say then that it's 15 times x, and then 57.5 times x minus 1.
Can you do that? I think I made a mistake with that. I don't think we can do that because
You can't. I don't think you can't do 1 minus x, but you can do x minus 1.
oh, I see what you mean. Yeah. Okay. But I'm just basing it off this diagram, right? But you guys get the idea of taking moments. We will do it on the other side as well. So just bear with me. So anyway, you have minus 15, and then minus 15R plus 57.5R, right? What we can do now is carry over, against we can carry over the 15, and then we left with a minus 15R plus 57.5, and if you do that, you get 42.5, right? 42.5R, is that fine? And then you just divide 15 by 42.5, and you'll get an answer of 0.3529 meters. Or 35, yeah. So what it means is that the point of the 1 point of contraflexure is now you have to say like one is going to be, how do I write? So it's basically 1.3529 from A. That's 1 PF, PF1, point of contraflexure. Point of, or you call it PC, it's called a PC, point of contraflexure. Yeah. And when I'm saying 1.3529 meters from A, of course it's 1 meter plus R, which is obviously found R, right? So what I like you guys to do now is do exactly the same from this side of the beam, right? In this case we have, so instead of calling this R, maybe we can call this guy, let's call this RS, let's call it S maybe. So now what you want to do is take moments at that particular point. So again, we have exactly, it's nearly the same setup. We've got 10, right, and then we have 47.5. So I'm going to give you guys 3 minutes to do that quickly, and then find out that distance. I got no mic powers, but if you throw your load diagrams, you can just measure it. Yeah, of course, but we don't want to deal with that graphical methods. It's possible, definitely. But if you want to go that way, no problems. Okay, guys, just take the moments at that point S, and see what you that's negative, plus a positive moment of 47.5 times, what's it? Times S. Yeah. That equals 0. You should get, let me get this right here. So it's going to be 10. And then we're going to have 37.5, I think. S, correct. And then we just divide 10 by 37.5, and we should get S will be 0.2667 meters. And then basically we're just referencing on from D. Then what can we say? Is it plus 1 also? It's quite simple. So 1.267 meters from D. Of reference, or from A if you wanted. And if that was the case, that would have been 1, 2, so 2 plus, or we can say, or 2.667 meters from A. Yeah, so you can say either or, same thing. Right? What's very important, students, again, you get a mark for the actual, of course you get a mark for your computation, your method. You get the mark for that, and a mark for that, and a mark for that, and a mark for that. So I'm just giving you a note. So you get the mark for the distance, for the position, and also your method. Okay, so I hope that was clear to everyone. That is your first shear force and bending moment diagram, some kind of lesson. So I'm going to do one more. Then yeah, I'll do one more now, and then I'll leave you with a practice problem. So let me just quickly go. Let me go back to our slides now. We will have a break, a longer break. Oh, let me just stop sharing this. So what I've shown you is a basic, I guess, obviously the concept of what's happening here and what really essentially happens holistically with these beams. So now I'll do a UDL. Here's a nice one to practice. And then I'll probably do this example, one with the cantilever, and we can practice that one, so we'll see. So we'll be okay for now. So let me tackle this example here. Okay. Let's prepare it. So it's all the same flow of questions, basically. Oh, wrong one. There'll be nothing new now. We've covered all what we need to do in terms of the theory. All a matter of getting used to different configurations. So yeah, let me just get back to the blackboard. Okay. So this question reads, so let me, yeah, okay, so for the beam shown, 6.15, through the shear force bending moment diagrams, again, find the position, magnitude of the maximum shear force bending moment, determine the position of the quantum flexure. So you can see that's all they really ask. They asked exactly the same stuff essentially all the time. So what's new is that you have a UDL, right? And I did mention you have to be cognizant of when you have a different kind of loading, pattern is going to change. So what's going to happen now during between A and B, our patterns will look something like this. Two triangles, in this case, it's not as simple as it seems, but you have two triangles and a parabolic kind of is it clear to everyone? A parabolic bending moment. Do we all get that? So be aware of the changing patterns. Students, are we all there? Students,
Can you repeat
you
what you said?
understand? So what I'm saying is now, when you have a UDL, right, you're going to end up with this kind of pattern. Your shear force will look like this now. You see there? Sorry. You've got that kind of thing, right? Your shear force is like these two triangles, and your bending moment will be this parabolic kind of curve. Are you with me? So now you must be aware of how the diagrams are going to look like. But you'll see what I mean. So when you do a bending moment diagram, it's just not going to be straight lines, if that makes sense. Okay. So let's try and see. So first things first, guys, compute the reactions. Can you guys do that quickly? So I'm not going to be doing reactions, but all I'll leave you with is RA. And Elisa, did you get what I mean? RA plus RC equals 4 times 12.
Yes, sir, thank you.
Yeah, you'll see. Plus 8. 4 times 12 plus 8. That's 46 kilonewtons. I think that's correct. Can you please mute your mic? Where is this now? So this is 56 kilonewtons, right? Okay. So can I please get my RA and RC value? So I'm just leaving it up to you for now. Oh man. Okay, just ignore this. It should take you around 2-3 minutes. It's very important that you get that all right. Let me just use white lines around. Oh, red is fine, man. Just use red, yeah, it's fine. Okay, ruler in. Can I have my reactions? Mr. Doyle, Mr. Romanus, Mr. Matasso, Aaron.
There's 28 for
Both.
Yeah, so for both of them it's 28.
Okay, yeah, that looks right. Okay, right. Throw this line over here. All right, beautiful. So 0. Okay. So now we do the same and walk with me through this. So shear force at A. At A we have one force, and that force is do I put like that? That's 28 plus 28 kilonewtons, right? At B, what do we have at B? Plus 28 minus how much? It's 4 kilonewton meter times 12, and that should result in how much? 20, right? Negative. At C, we've got 28 minus 4 times 12. What's the other one now? And oh yeah, you've got a plus 28 again. So therefore at C we only have minus minus 48. Correct. No man. What am I doing here? Oh, it's not minus 48, it's plus, sorry, it's plus 48. 28 times 2 minus 48. 8 plus 8. And a D, that should all balance out and be 0, right? You can check 28 minus 48 plus 28. And of course, that'll be a negative 8, which gives you 0. Must close. Must close. Students, are we all happy with that? Any questions of the shear force? Please ask. We will be coming back to shear force and bending moment. You do have a good YouTube channel, but I mean, are we all there? I'll give you guys 2 minutes to just let me know if you're fine. Students, please get it done.
Oh, this is I forgot the basics here. So how do you get that 28 kilonewtons?
So is the reaction at C equal to 8?
There.
Oh, so you know what the moments, like you mean the reaction itself?
Yeah, yes, I know it's a very basic question, but I forgot.
Okay, so with the UDL, right? Remember, the first thing we have to do is say it's kilonewton per meter, right? So it's 4 times 12, right? And we know a UDL acts at the center of where it actually is, where it's over the span it's covering. So it's 4 times 12 will give you 48 kilonewtons. That's the first thing. So 4 times 12, that's 48. Is that okay? And where x is the distance, the midway between the span is covering, right? So then basically you can treat the UDL as a point load. From there, it should be fairly easy. I don't know if you're with me.
Okay, no, I got you.
Yeah, so that's going to be RA and then RC, and you're just going to take moments. And Elisa, your question?
I was asking, did you get 8 or 28 for C?
That's 8. It should be
I
8.
get 28.
So just checking that, Elisa. So at C, remember you have 28 going up, right? And you've got minus 4 times 12, which is 48 going down. And then at C, you've got another 28 coming up, remember? So 28 times 2, the both positive minus 48. It's 8. You got it?
Are you doing sum of forces in the Y or are you doing moments?
It's sum of forces in the Y. For shear force, we only do not moments. Remember, shear force is just forces. Sum of forces in the Y, in the vertical. This is shear force. Are you there? Shear force, not moments yet.
So is it wrong if you do it by moments?
Yes, basically. With moments, you do for the bending moment diagram. So shear force, you're just looking at all the forces, like I said, from left to right. Are you there?
Okay.
Are you with me, Annalisa? Should I redo over the shear force diagrams? Are you? Is everyone?
No, it's
Can
okay.
everyone get?
Okay.
Okay.
I'll catch up.
So at A, we've got 28 going up. Now remember what I said here, right? That because it's a UDL, it's gonna go down like that. So the load is, you've got a positive shear force and negative shear force going down. However, at B, we had 20, right? So we don't go 20, so it's going to be at 20 here. So it's not equal length. So one is like probably small, one side is small down. So that's 20 over here, right? And then we have 20 continuing for that from B to C, and then at C we go up to 8. We're up to 8 kilonewtons, and then eventually that carries a positive 8 kilonewtons and then goes down again to 0. So what I'm saying is, if this force, if we didn't add that extra 20, this extra 28 here, this should have been 28, but of course we have at this point. What's important? Okay, this is not looking how I want it. So maybe I should call up my beloved ruler. Make sure you get the. Just want to get that line again. Just give me a second here. And then yeah, so my ruler. Okay, cool. Ruler. I'm just gonna have to adjust my force a bit here. Just bear with me. Perfectly straight line. Perfectly straight line. Yeah, so that's important is that shape, guys. Right, there we go. So then you can say bye to that guy. Yeah, so here we got 28, 28, and then 0. Of course, this is minus 20, obviously. That's below the line. So again, looking at this, our maximum shear force experienced will be here. So we load this beam up, it's most likely to break at that support over here in terms of shear. But of course, this is a fairly long beam, so shear is a very small thing. So that's our maximum shear force. Again, if you want B, we've already located our maximum shear force, and it seems to be at A already. That's 2 marks free for you there. Okay, so let's do the bending moment diagram now, right? So let's take moments. So this is where you want to take moments. Okay. Ruler. Okay, make that a 0. Okay, so guys, I want you to take moments at A, obviously, it's gonna be 0. Can someone call out the moments for B for me? Students, let's get the moments. Students, moments at B. All right, guess no one is alive today. So at B, we've got two forces acting. So the first force is the RA, and RA is at 28. That's 28 times 12. That's going upwards, and then you have the 48 minus 48 times 6, right? And then moments at B yield a result of 28 times 12 minus 48 times 6 to give you 48 kilonewton meter, right? And then we take our moments at C, and that's going to be 28 times 16 minus 48 times, that's 6 and a 4, and that's times 10. And that's 28 times 16 minus 48 times 10. And if you get minus 32, then moments at D, so you got 28 times 8, not times 8, sorry, times 18, no, 12, 20, is that 20? Yes, 48 times that's 6, that's 16, plus 28 times 4. Am I doing this right here? 28 times, is it 20 meters? 12 and 4, yeah. Minus 48 times 14. Sorry. Yeah, oh, then 28 times 4. 28 times. Students, are you guys still there? Because you guys are awfully quiet, eh? 48, 4, 4, 6. Something doesn't add up. Let me just check here. Is there any questions? Is anyone lost? Because people are like dead quiet here. Hello?
So I'm lost because in the first one,
Okay.
when we're finding the reaction forces, we use the sum of moments. And then in the second one, I'm not sure what you did.
I said for the reaction forces.
Yeah.
Like I said, that's up to you guys. So are you guys unable to find the reaction forces? Is that what's killing you?
Yeah.
But are you able? Do you understand the shear force in bending moment diagram? You get that?
Yeah. Yeah.
Okay. So I'm gonna just do this. Like I said, this is supposed to be known by you guys, and honestly, this is like super easy. But I guess maybe it depends on who taught you. Anyway, so you've got 8 kilonewtons there. You've got RA going up here, and you've got RB. I'm sorry, RC here, right? You know, for UDL, we take 4 times, it's kilonewton per meter, right? So over the span, so that's 4 times 12. You get that? So that's 48, and it acts in the middle. So that's 6 meters here, 6 meters there, 4 meters. Wait, 6, 6, 4. Oh, wait, yeah. So I'm out here. Just give me a second. So 6 from here, it's 4 meters. That's where C is. Just delete this. So from here to here, 4 meters, and then another 4 meters here. Right. So this is 48 kilonewtons. That's RC. So taking moments about C, right? It's going to be RA times 6 or times 12 plus 4, which is 16. And then we have taking moments of the 48 kilonewtons, that's 48 times 6 plus, that's 10, right? And then at C we also have the what you call it, the 8 kilonewton on the other side. So that's 8, Let's go in clockwise, 8 times 4, and that equals 0. Then we can solve for R. Hey, are you happy with that? You understand that? Yeah, so that's basically all times 10 minus 32 divided by 16. And you should get 28 kilonewtons.
Okay.
And
I
of
see my
course, now I
mistake.
can take moments on the side. Yeah, that's all. And then so
I
now for
swapped.
your back to your, excuse me?
I swapped A and C. That's my mistake.
Oh, I see. So then if you're taking moments over here, that's 28 times 20 minus, what was it again? 48 times, that's going to be 6, 14, and then plus 28 times 2, and you should get 0. Your moments at the end always should be 0. So if you're going to sketch this diagram, again, you need to know and be cognizant of this diagram over here. And when sketching a UDL, the shape is parabolic or has a curve, right? And then, so that means it goes like, so start at, so B is at 20 kilonewtons, right? Where's B again? B at 20. So B is, no, what not 20, sorry man, B is 48. So we know that this goes like this. It ends at B. Okay, so it goes something like this. So B goes like that. And then C is at 32, minus 32, so that goes down somewhere there. And it goes back up. So this is minus 32 kilonewton meter. And this point over here is at 58. But now we're not done yet because with the shear force is 0, I mentioned to you. So this peak's supposed to line up here. So just give me a second. The bending moment's at the maximum, right? So it goes up like that. So make sure you get that done correctly. So now what we need to do is locate the position of where the maximum bending moment is. It's not 48, it's at that particular point. Do you guys understand? Force, I'm sorry, the distance with the shear force is 0, which will yield the maximum bending moment. Okay. So what we do now, we need to now locate that particular distance. Okay. Serious, I can, yeah, go for it.
So you can hear me?
Yeah, I can hear you now.
Yeah, they say that when you make that bend, that kind of a parabola thing, that for your bending moment, that is
Yes.
it not like in the middle? Is it not already like in the middle of the distributed road, like at the at the 6?
Yeah, very good observation. So now let me tell you something. If I'm gonna do a scenario, if you had a diagram like this and you had the UDL like that, right? Then your bending moment diagram will look like this. Exactly like that. It'll be exactly in the middle. But remember, in this case, you've got, it's not over the whole span of the beam, so you've got other forces acting up. That's why it's not shaped perfectly like that. So it's not exactly in the middle. You understand? So that's a very important question. If it was covered the whole span of the beam, but in our case, we don't have that. We have now, remember, an extra support over here. Are you with me?
Yes, sir, I am with you.
That's why. But in the circumstance where it covers the beam fully, for instance, I'll show you maybe when you do this example yourself, let me find one here. Give me a second. Do I have one like that? Let me just check. Yeah. Okay, no, but this one's also not like that. But if we have a UDL completely like that, then it will be like that. Maybe I'll give you an example with a complete UDL like that. So I'm just letting you know. That's why it's not perfectly. So what we do now, we have to locate where the maximums, where the shear force is 0, so we can find the location of the maximum. Right? And so, because now, so how do we do that? We actually know the maximum bending moment. No, we don't know yet. We still have to find it. Okay. So we go to our shear force diagram. I'm just going to paste that now. So our shear force diagrams over here. So now we need to find this distance here. So that lines up with the maximum, and you see how we get the 98. So we need to find this distance. So now what we do, we can call this maybe X or whatever again. At point X, just move this to the side. We have to now say we take our shear force at X. So again we have 28, right? But now our UDL, remember here, our UDL is not now completely 12. Can someone tell me what is a load now for the UDL? That's force times distance. What is it? It's load times distance or span. And what is the span? Mr. Kiefer?
Is it 48?
No, it's 4 times X. So we say 4X. Then we make it equal to 0. That's all the forces acting there. We carry over the 4. We have 28. And then we say 28 divided by 4. And we're going to get 7 meters. So 7 meters from 8. Right? So now we've located where the maximum bending moment is. A max is at this. Is that clear to everyone before I move on? Students, is that clear to you? Oh, no questions. Hey. Any questions? Now, I'm going to leave this up to you.
How do you get the 98 kilonewtons there? Sorry, I was busy writing when you said.
You're still getting there. I'm more concerned about finding the distance. Yeah.
Are you just getting the distance now to X?
Yeah.
Okay.
Now, I'm going to see who's sharp here. So if we found the distance, right? 7 meters. How do we find the moment at that particular section at X, which is the maximum bending moment position? How do we normally do it? How do we take bending moments at a particular point there? Can I say moments at X? Don't we say, Mr. Doyle, minus 28 times 7? Are you correct? Plus.
It depends on how you've taken your signs for the whole time. If you're taking counterclockwise as positive,
sorry,
then yes,
so that's
correct.
plus. Yeah, that's plus minus 4 times 7, which is the whole span of that X, times 7 over 2. Remember, this is just a force part, and that's the distance. That's a moment. And then we can get our moment at X. So we compute that. We get 98 kilonewton meter. You see? For instance, if I had to find a moment at, so this is, um, 28 times 10, and then we can say minus, that's going to still be now 4 times 12, which is the total UDL. And then we're just going to say that's 6. So that's, oh, at 10, right? So I can't say 12. So 4 times 10, and then 10 over 2. So I'm just showing you at a random position what the moment will be. And that's going to be 80 kilonewtons. And that's going to fall somewhere here. That's 12, 10, that's around there somewhere. So 80 kilonewtons is around here. Students, are you still with me? So that's how you're going to find the position on the maximum bending moment if you can't find it. Yes, Mr. Doyle. Are you speaking? Okay, so just to end off this part of this section, can you guys find me the point of contraflexion over here? We're going on a break soon, don't worry. You can also find the area on the triangle, that's also acceptable. I just don't like that method. That's fine, Zach, you can do that. Yeah. So can you find the point of contraflexion for me at G? I give you guys 3 minutes to do that because we're going to break at 1 o'clock and then you'll return at 2. So what's it, 1 point of contraflexion? Here's the guys who's always Mr. Silva, Mr. Mataso, Mr. Zuma. Come on, guys, man. Simple. 5.6 meters.
So, like, I'm lost. I just wake up late. I didn't follow the.
Oh,
I miss everything.
Fine.
Yeah. I'll go through later. Yeah.
So, Mr. Bethany, how did you get to? Is it 5.6 meters from? D. Where is D? 5.6 meters from D. Is it possible? No, yeah, it's possible. Yeah, that's right. How do you do it? Can you explain to us? Can you write it out here? Saying moments at G. It's just too much to absorb today. Moments at G equals 0, right? So then we say 8. Okay, you're saying something? Okay, great. So we can say 8 times, what's that distance there? 4 plus x, right? Let's call that distance x here. So that's 4 plus x. Then of course we're just going to have also that's negative, plus 28 times x equals 0. We have minus 32 minus 8x minus 28x equals 0. So we can carry 32 on the other side. I feel like, oh, this is supposed to be positive. It's a positive moment, sorry. And we end up with 20, I think. 20x. And then we can say 32 divided by x. So 32 divided by 20 will give us 1.6. Right? So we know that's what x is 1.6. So we add the 4, that'll be 5.6 meters from D. Because we've determined x to be 1.6 meters. Oh yeah, no, I do apologize. Okay, guys, any questions with that? We're trying to find the point of contact lecture because we're going to go on a 1-hour break and then we'll continue. I know it's much to take in, but we're all worth it. And don't worry, you have a good YouTube channel to refer to, which we'll figure it out. Any questions on me taking moments at that particular position? That's exactly the same as the one before.
Yeah, so I'm most confused around the some of the moments about x, where you have 4 times 7 over 2.
Yeah, so with the door, like I said to you, right? So if we found x, right? We know x is 7. Are you happy with that first? Can we agree on that one?
I'm relatively happy.
Yeah, okay. So we need to find if we need to find out the moments at that point. Don't we just say, like on the previous parts, 28 times 7? That's a clockwise moment. Are you happy?
Okay. Yeah.
And then we say 4 times 7, that is 4 times 7, which is the load part. That's 28. Yeah. But remember, the UDR acts halfway between the 7, right? So that's why it's 7 divided by 2.
Okay. No, I've got you. All right. It's 4 times 7 to get the force, and then it acts halfway between the two. Okay, dokie. Thank you.
So what I was illustrating over here is now we can even find it at 10 using the same kind of idea. Okay, next question. Someone had their hand up now.
Yeah. Can you just explain to me on bending moment of 32 equals to the 32 8 times 4 plus x? That 28 part, 28 times x part. Can you just explain to me again?
Okay, so remember here, looking at this here. So remember, students, well, you're taking moments at this point here, right? So the first force is 8 kilonewtons, right? And that's 8 kilonewtons. That's 4 plus x. That's the first distance. But of course, that's negative. But remember, we have another force here at 28. And that 28 is covering this distance. So that's why 28 rotating that way, 28 times x. Do you see? And that's positive because it's going, that one is going clockwise and anti-clockwise. I could have just changed the signs there, sorry. So this is actually positive and that is negative. That's the same thing. Yeah. Shilas, do you have it there? Are you happy? Make that positive, positive, make that negative.
Yeah, I see. Yeah, I see.
Yeah. Okay, guys, we're done with this first part of the lecture. Please don't eat too much. We have to now continue with a few more examples after this. Okay, see you at 2 o'clock. Cheers.